We're now going to take a look at the derivative of the sine and cosine functions. Now these functions are so common in mathematics and all fields of science, physics, biology, chemistry, also economics and business, that it's obvious that we would want to know what their derivatives are. So we have a theorem which states that the functions sine x and cosine x are differentiable for all real numbers x, and the derivative of the sine function equals the cosine, and the derivative of the cosine is negative the sine. So that's actually pretty easy to remember. They just sort of flip-flop. The only thing you have to remember is that the derivative of cosine is negative sine, while the derivative of sine is positive cosine. So you just have a sign change right there. Now we're going to take a look at two graphics down here that illustrate why these results hold. Then we'll look at some examples, and then we'll prove rigorously that the derivative of the sine is the cosine. And the proof of derivative of cosine equaling negative sine is similar, but we're not going to go over that one. So let's take a look at this graphic down here. First of all, we have the graph of the sine function. That's the blue curve right here. And if we look, we have a line right here, a red line. That is representing a tangent line to the graph of the sine function at a particular point along the sine curve. And what we're going to do is we're going to let this tangent line slide along our sine curve and keep track of its slope. And we're going to plot its slope out, and then that'll give us the graph of the derivative function. So let's start right here. Let's actually move that line back a little bit right there. Now you notice at this point right here, if you look, our slope, the slope of this line is currently equal to 1. So on the graph of the derivative, we would put 1 right there. Right there's 1 on the y-axis. So we would plot that point on the graph of our derivative function. So that point is on the graph of the derivative. Now we're going to let this line slide along the curve of sine, and let's see what happens. So you see the slope is decreasing right now. The slope of that line is decreasing until we get to this point right about here. Now let me stop that there. Alright, now you notice right here the tangent line is horizontal, so our slope is 0. And on the graph of the derivative, we would then drop down and plot the point. That point right there, its corresponding y-coordinate is 0. Right there's 0 on the y-axis. Now this point is currently that's actually at the x-coordinate of that point is actually pi over 2. See, 1.57. It's a little hard to read there, but that's 1.57. And the y-coordinate is 0. The y-coordinate here being the slope of your tangent line. Alright, so now let's let that line continue to move along. And right about here, now, we see that the slope is negative 1 of this red line. And so we would plot negative 1 right there. The y-coordinate, see, negative 1, would be plotted on the graph of our derivative function. So we have this point, this point, this point, and now we let this slide along a little further. Now right here, our slope is 0. And we would plot that point on the graph of our derivative function. Note the y-coordinate of this point being 0 on the y-axis. Alright. Now let's continue. Let's go to our next point of interest. That would be right over here. Right there, you see our slope is currently 1. And so we would plot 1 right there. That we would plot that point. Notice that has a y-coordinate of 1. And then continuing right to this point. Alright, so right there, that line has a slope of 0, so we would plot this point on the graph of our derivative function. Notice that has a y-coordinate of 0. And in this manner, we recover our derivative. Notice it's this gold curve right here that I'm tracing out right now. It's this curve right here. We just connect the dots. And what does that look like the graph of? Well, that is the graph of our cosine function. It looks exactly like the graph of cosine, and that's exactly what it is. So that's graphically why the derivative of the sine is the cosine function. Same thing for the derivative of cosine being negative sine. If we look at this other graph over here, so right here, the blue curve is now the graph of the cosine function, and we will let these tangent lines slide along its curve and plot their corresponding slopes. So right now you see the slope of this line is 0. So I would drop down, keep the same x-coordinate, drop down, and right there would be a point. The y-coordinate of that point is 0. So that point would be on the graph of my derivative function. And then we just continue. Right there, our slope is -1, so we would plot -1 right here. The y-coordinate of that point is -1. And then just continue. Right there, our slope is about 0. We would plot a point right there with a y-coordinate of 0, so that point would right there would be on the graph of our derivative, and we just continue like this. Right there, our slope is 1. We would plot a point right there, go straight up, plot a point with a y-coordinate of 1, and we just continue in this manner. And you notice the graph that we get, this graph right here, the gold graph, that looks like, well, that is negative the sine. It's the sine function just flipped about the x-axis. So this graph right here is y equals negative sine x. And so that's graphically why the derivative of cosine is negative sine. All right, let's take a look at some examples. So let's evaluate the derivative of y equals pi times the sine of x plus the square root of x. So dy dx, so we want to look at so what this is going to be, it's going to be the derivative of pi times sine first plus the derivative of the square root of x. That's by our basic rules for differentiation. The derivative of the sum of these two functions is going to be the sum of their derivatives, so we take their derivatives individually. Now let's write that out first. So now when we look at the derivative of this piece right here, the pi is just a constant, so it can be moved outside. So we end up with pi times, and then we have the derivative of sine. And remember the square root, that can be written as x to the 1/2. And now we can differentiate everything. So we're going to have pi times derivative of sine is cosine. And the derivative of x to the 1/2 power is just using our power rule. And then we can just clean that up as And there we go. That's our answer. Let's take a look at another example. So let's evaluate the derivative of y equals 2 sine x plus cosine x, and then find the equation of the line tangent to the graph of this function at the point pi negative 1. And then we'll verify our answer graphically. Alright, well, dy dx. So we're looking at d dx of and then of course we can split this up and also pull that 2 out at the same time. Derivative of sine is cosine. And derivative of cosine is negative sine. So we'll write this as minus sine x. And that's our derivative. Now to find the equation of the tangent line at the point pi negative 1, well, we have to find the slope. So the slope of our tangent line is going to be dy dx evaluated at pi, the x-coordinate of that point. And that is going to be 2 cosine of pi minus the sine of pi. Now you have to remember, cosine of pi is negative 1, and the sine of pi is 0. And so that's negative 2. So there is the slope of our tangent line. So the equation of our tangent line is then going to be y minus negative 1. And then we can clean that up as just realizing that this is positive 1, take it over, you get negative 1. And there is the equation of our tangent line. If you plot on your calculator the graph of 2 sine x plus cosine and this line down here, you will get a picture that looks like this. So the blue curve is the graph of 2 sine x plus cosine, and that line right there, which does look like it's tangent right there, that is the point pi negative 1. That gold line is the graph of your tangent line down here. Alright, let's take a look now at the proof that the derivative of sine is cosine. So we want to prove that derivative of sine is cosine. Now before we begin, we need to recall some results. So let's remember that we have a trig identity. Now this one you may not remember, but it's true. The sine of the sum of two angles, alpha plus beta, is the sine alpha times cosine beta plus cosine alpha times sine beta. That's a fact. It's a trig identity. We're not going to prove that. We're just going to assume that that is true. And it is true. Also remember this from our discussion of limits. Limit as x approaches 0, sine x over x is 1. And limit as x approaches 0 of 1 minus cosine x over x is 0. We need those two results. Now, with all three of these, we can begin our proof. So we start out with now what we have to do is go back to our limit definition. This is why we studied the limit definition, because all these proofs that we do, we have to use the limit definition for the derivative. Now what we're going to do is we're going to split this sine function up. We have sine of x plus delta x, so the x is like our alpha, the delta x is like our beta up here, and we're going to split this up using this identity. So we're going to write this as and now what we're going to do, we're going to combine the sine x and the cosine delta x with this sine over here, and then we're going to just take this term and leave it as is, and we're going to split this fraction apart. So watch what we do next. So what we did here is we combined these two terms, this term and this term, with a negative. We factored out a sine x, so that all is right here, right up here. That's this term. Notice I have the sine x factored out, so if I multiplied the sine x back in, you see I'd get sine x times cosine delta x, that's this one, minus the sine of x, all of that's over delta x. And then this term right here, I have cosine x times sine delta x over delta x, and that is right here. And we just pulled the cosine out in front of this fraction. That's all we did. And we also split the fraction apart, right? Using the fact that a plus b over c equals a over c plus b over c. Right, so we split it apart like that at the same time, where the c is our delta x. Now let's take note of this. As delta x is approaching 0, this term right here is going to 0 by this rule right here. Now this rule is written as 1 minus cosine x over x equals 0 in the limit, but you could interchange the cosine and the 1. You know, if you just multiplied this by negative 1 right here, put a negative 1 right there, negative 0 is still 0. So we just have it flipped down here, but it's still going to 0. And the sine delta x over delta x, well, that's going to 1. And so what you have here in this limit, you have the sine of x, that's this part right here, times 0 plus cosine of x times 1, and of course this is just going to be the cosine of x. And there we go. We've just proven that the derivative of sine is cosine using a trig identity and the two previous trigonometric limits that we looked at. And that's why we considered those two trig limits earlier when we were studying limits, because they're so important, because they're used to evaluate the derivative of the sine and the cosine functions. That's why we studied them. Alright, and that does it for this lesson on the derivative of the sine and cosine functions. And later on, when we have a few more tools at our disposal, like the product rule and the quotient rule, we'll be able to evaluate the derivative of the other trig functions.